We started this project by first tackling the minimum requirements. The goal was to be able to downsample the images, compress, and transmit within the 75 seconds of transmission time, and eventually reconstruct by upsampling on the receive end.
In the initial phases of our project implementation, I was able to work with Princeton to work towards getting a better idea of what downsampling factors in space and time would help us out. And we figured that downsampling in time compromised the transitions between each frame a lot, and that would decrease the accuracy of the video we were trying to decode. So we decided to go with downsampling in space.
After Merriam and Bronston found the effects of downsampling in time and space, we needed an algorithm that would find these downsampling factors for any given video. And I worked on writing the algorithm that could look at the pixel size of the original video and find the best downsampling factors. We're then able to transmit these factors with our packets.
We modified the APRS packet to contain information about the frames as well as the decimation factors in the source and destination fields. We transmitted call sign information in the digi field. In order to achieve this, I had to modify the newax25.py library in order to accommodate the new information in the source and destination packets. This was because the existing library used a call sign encode checker in order to ensure that the call sign was well formed for source and destination. However, since our data was not a call sign, we had to modify that library in order to support our new use case.
Meg and I were able to also work on the windowing functions that would work well to avoid alias defects in the video, as well as gzip compression so that we could reduce the time spent in transmission.
By switching from unsigned integers to unsigned shorts, I was able to save some bytes, and so I was able to stuff 3 numbers into one of the source and destination fields for the frame size, and I was able to stuff another 2 extra numbers into the other field for the downsampling coefficients.
To implement the color space transform, we first defined an invariant transformation matrix that would convert a 3-dimensional RGB vector responsible for 1 pixel into another 3-dimensional vector with luminance and 2 different types of chrominance. We then applied this transform on 8x8 chunks of an original frame. We separated out the different luminance and chrominance values and downsampled only the chrominance values, such that what used to be an 8x8 chunk became a 4x4 chunk. This allowed us to minimize the amount of transmitted information while retaining as much visual quality as possible. This retention of visual quality is possible because the human eye only really cares about luminance.